Let's start it. Share my screen, please confirm my voice is
Hello. Hello. Good evening, sir.
hi. Is
Good
my
evening, sir.
voice is it fine?
Your voice little not audible, sir. It is very slow.
Okay. Let's change my audio device. So now is it fine? Is it audible? And is my screen visible? Okay. So last lecture we were in the last session we were seeing about what are known as desaturation based protection schemes, right? So we will start off from there once again. So can you please confirm if my voice is audible?
Yes, sir.
Yes, it is audible.
Okay, thanks. So I'll just open my slide and yeah, okay. So in the last class as well, we were seeing about desaturation based protection schemes, correct? Let me see if my camera turns on. Just a second. I don't know why the camera is not appearing, but yeah. Okay, so let's continue with the DSAT based protection scheme. Correct. So we were seeing that so under completely turned on condition of the device, right? So in the completely turned on condition of the device, the MOSFET channel can be approximated as an channel resistance, correct? Which is RDS on, correct? So this is basically just the MOSFET model. Let me draw in. Okay. So and then we saw that the DSAT scheme kind of measures your on-state voltage or the voltage across the device, which is VDS, correct? So the idea was that, see, if we can go back a few slides, yeah. So the idea was that under um, normal operation of the MOSFET or IGBT, you are expected to operate somewhere along these violet colored lines, right? That is in these regions. It can be over here or it can be over here, somewhere over here, correct? So this is during normal operation. And during what is known as uh, and what you see is beyond a point in VCE, there is a shift over here, right? There is a change in the slope. So we saw that for MOSFET and IGBT, the nomenclature is kind of a little bit different. That is in the sense that for MOSFETs, you call this region as the ohmic region, correct? Ohmic or the linear region, correct? So this is your linear region. And beyond the point, there will be a transition towards the saturation region, correct? So this is for MOSFETs. And for IGBTs, we also saw that the nomenclature is kind of a little bit different in the sense that the violet colored region is called the saturation region for IGBT and the yellow colored region is actually the linear region. But nonetheless, the idea is that you want to operate somewhere over here where the MOSFET channel or the IGBT can be approximated like a linear resistor, right? That is an RDS, right? So if the voltage drop goes beyond a particular point, then you see that the current kind of saturates. So you transition from the violet region towards the yellow region, correct? So in terms of nomenclature, you are leaving the saturation region for the IGBT and going towards the linear region or what is known as the desaturation region. So the idea is that you want to sense that the device is actually leaving this region and going into the desaturation region or the linear region, and based on that you want to take protective action. So you understand that the idea is to measure VCE or the voltage drop across the device, VDS for MOSFETs. Correct? So what we saw was that we can have something like an op-amp based comparator, correct? So I will measure what is the VDS or VCE across the MOSFET or IGBT, and I will compare it with the reference value, right? So I will compare it with the reference value, and if I sense that my VDS or VCE has exceeded the reference value, then I would be generating a fault signal, correct? So what is the V reference? V reference corresponds to the point at which there is a transition, correct? So you see that this is the point at which there is a transition. This is the point at which there is a transition. Correct? So you know this is for increasing values of gate source voltage, right? So this is so so this is VGS1, VGS2, VGS3, and so on. So this is for increasing values of the gate voltage. And you see that, let's say you're operating at 15 volts, right? 15 volts gate source voltage, which means that the curve corresponds to this, right? Let's say the 15 volts curve corresponds to this. 15 volt gate voltage curve corresponds to an output characteristic of this, right? Green one. So now you know that as a ballpark figure, this is somewhat This is the point at which there is a transition from your saturation region to the linear region in the IGBT, right? So if I can just extend this to the x-axis, so what you would be seeing is this point, right? So this becomes kind of your reference. So you know that if the voltage increases beyond this point, it obviously signifies a fault. Okay, that means that you have entered into the saturation region. You don't want to operate over there, right? Sorry, you have entered into the linear region. Okay, because you know that beyond the point, what happens is kind of the voltage goes on increasing. So hence there will be a huge power loss across the device, correct? And it can cause heating. So this is kind of the transition region. Okay. So you measure it with you compare it with the reference value using a comparator. So the comparator would now be giving a logic high pulse. Right? Comparator would now be giving a logic high pulse. So what you do is next you take the output of the comparator, give it to a NOT gate. So if you get a logic high pulse over here, obviously you will be getting a logic low pulse after the NOT gate. Okay, and I will AND this using an AND gate, right? This is an AND gate. So I will AND the NOT of the comparator with the microcontroller pulses. Okay, so if the output from the comparator goes high, then the output from the NOT gate goes low, and therefore irrespective of whether you get a high or a low from microcontroller pulse, the output would obviously go to low immediately. Correct? The output would go low immediately. So the idea is that this protection scheme is independent of your microcontroller operation. Even though your microcontroller may give continuously pulses, if you sense that there is going to be a fault, then obviously the output from the comparator goes low, and therefore the output from the AND gate goes low. Okay, this actually goes to the gate driver. And under normal operation, you can understand that the output of comparator is logic low, and therefore the output of the NOT gate is going to be logic high. Therefore, whatever you are going to AND with the microcontroller pulses, you will be getting the same microcontroller pulses, right? This is during normal operation, right? So this is logic low, and this is logic high. You get the microcontroller pulses as it is. Okay, fine. And all of the circuitry is not something that we do externally. So this comparator part and the AND gate part, all of these come embedded within the gate driver IC nowadays. Okay. So within the IC, you will be having all of these. Okay. We will be seeing what is the internal circuitry inside a gate driver IC. Probably I can also explain to you guys using a commercially available gate driver IC. But idea is the circuitry would be something like this for protection. Okay, so we saw that there is going to be a comparator part. So then we also saw that we cannot directly connect the comparator. Correct? We cannot directly connect the comparator. The reason being that, so what would happen is, let's say, consider this half-bridge circuit shown in figure. So in that case, if Q1 is on, right? If Q1 is on, then the entire VDC would be appearing across Q2, correct? If Q1 is on, entire VDC, which can be very high values like 400 or 800 volts, they may appear across your Q2. Okay, so then since you are directly sensing the voltage across Q2, then what might happen is that your entire VTC voltage is going to appear across the comparator, and it will result in a catastrophic failure, right? So the idea is you don't want this overcurrent protection circuitry to kind of operate when Q2 is high, or when when the voltage across Q2 is high. Okay, that is when Q2 is turned off. So because it doesn't make any sense to measure or sense overcurrent when the device itself is off, right? So there needs to be kind of a clamping mechanism or kind of a protection mechanism which will make sure that this circuitry is disabled from being directly connected across Q2, right, when the device is off. So when Q1 is on and when Q2 is off, then what will happen is your voltage across the device, VDS, is going to be VDC, that is the DC bus voltage. And you don't want the VDC to appear across this terminal, correct, across the comparator terminal. So what people thought was a simple but effective solution, that is to use a diode over here as shown. Okay. So you put a diode in kind of a reverse condition with this being your cathode and this being your anode. Okay. So you can understand that if you're going to have around 400 volts or 800 volts over here, right? Obviously, this diode will be in a reverse bias condition, and therefore the same 400 volts will not appear over here. Rather, this diode is going to block 800 volts or 400 volts. Okay. So this diode will be blocking 800 volts and 400 volts. You know that the operating quadrant of a diode is in the second quadrant, right? That is, it can block reverse voltage and conduct positive current. Correct? So it can block reverse voltage and it can conduct positive current. Right? This is the operating region of a diode. So basically, you wanted to block 400 volts and make sure it doesn't appear across your MOSFET. And at the same time, you also wanted to make sure that during normal operation, it should be turned on. Right? Okay. So this is your V, this is your minus V, this is your I, this is your minus I. Okay. Right. So what we saw, we had a comparator. We
Excuse
compared
me.
based on
Hello.
your device output characteristic. So V reference is fixed based on device output characteristics. Device
Hello. I have
output.
one small doubt. Hello.
Yeah.
Yeah. Yeah. When Q2 will be off, that time this 400 or 800 volt, if it is comes across the drain to source, the polarity will be from source to drain, huh? Or drain to source.
No. It will be from drain to source, na. See, the MOSFET cannot block reverse voltage, right? Because of the antiparallel diode. See, you understand when Q1 is on, right? So let me take another figure or another slide, right? So the circuit we are having right now is so we label this as Q1 and this is Q2. Okay. So when Q1 is on, correct? Obviously Q2 is off. Correct? So in that case, your equivalent circuit can be something like, let's assume Q1 is short, right? And then Q2 is this switch over here. So, okay, so let me not draw a generic switch. Let me take so Q1 is on and Q2 so this is your drain, this is your source, this is your gate, right? So what happens? You understand that voltage across VDS is going to be VDC, correct? When Q1 is on, right? So this is what is going to come across your protection circuit, and this is something that you don't want. That is why we put a diode something like this, so that even if you get VDC over here, the diode kind of doesn't get forward biased. Okay. So since you're having a diode, you're kind of clamping the voltage across the comparator.
Okay, but when Q2 will be on, that time whatever this reference voltage it will compare with respect to the VDS, that time what will be the polarity?
Polarity of what?
Means when Q2 will be on, that time we are monitoring the VDS, na, with respect to some reference voltage. So that time what will be the polarity? Because still that if it is positive, then diode also it will block, na.
Yeah, so I think we saw this in the last class as well, right? So see, okay, I'll just come to that. Anyway, I'm just recapitulating how we came to the circuit. So you're right in the sense that when Q2 is on, even that time there will be some VDS voltage based on I into RDS drop, which is again positive, right? So your question is, how do we make sure that during that time alone the diode is not into the picture, right? That's the question, right?
Yes, yes, yes.
Yeah, yeah. So this is something I'll just go to that next. Okay, fine. So this was during Q2 turned off condition, right? So during Q2 turned off condition, the idea was to make sure that your VDC doesn't appear across your comparator. And second, anyway, I don't want the circuitry to operate when Q2 is turned off because it's basically an overcurrent protection scheme, and there is no question of overcurrent when the device itself is off. Okay, so this is during turned off condition. But as you asked, what happens during turn on condition, right? So what people did was they came up with a circuitry to make sure that this diode kind of turns on during that scenario. Okay, and how would this diode get turned on? That's the next question, right? So what is ours? Let's see. You're going to get some VDS over here, right? You know that this during when Q1 or let me take the slide once again. Yeah. So correct. So I can approximate this something like this. Okay. So this is your RDS on, and you will be having a VDS. Okay. So ideally, what would be this value of VDS? So this value of VDS, ideally, when there is no overcurrent as such, let's say this is your reference, right? This is your reference for the device transitioning from your kind of ohmic region into the other region, correct? That is the flat region. So you know that under normal device operation, you are going to lie somewhere over here, correct? You are going to lie somewhere over here. During normal operation, if there is no overcurrent, you are going to lie somewhere over here. Same for MOSFETs and IGBTs as well. You are going to lie somewhere over here, correct, for MOSFET. That is somewhere in the ohmic region. And if you're in the if you are operating an IGBT, then you are going to lie somewhere in the saturation region. Basically, you're still in this kind of linearly increasing kind of curve, right? And when there is going to be an overcurrent, then what would happen is your VDS increases beyond VREF, right? If VDS increases beyond VREF, it signifies an overcurrent, or in other words, a short circuit fault. Right? So again, what is going to happen is that you are going to go beyond the VDS reference point. So by common sense, you can understand that when would this diode get turned on? Your diode will get turned on only if you have a voltage over here which is more than this voltage, correct? Which is more than VDS. Only then the diode can get turned on, right? Right. So how do you do that? So point is you need to have some kind of an arrangement which makes sure. See, the point is you don't also want to have the circuitry enabled only when there is an overcurrent. You want the circuitry be enabled during the entire time of your device turn on condition, right? That is for the entire duration the device is turned on, or for the entire duration there are gate pulses, you want the circuit to be enabled or connected across your drain to source, right? So that is when people came up with this kind of an arrangement. So we saw that. There will be a signal level MOS over here as shown. Okay. So there will be a signal level MOS over here, correct? So, and we also saw that this MOS is going to be, yeah. So let me go to this. Okay. So this MOS is going to be fed with a pulse which is not of your actual gate pulse. Okay. So if this is your gate pulses that you are giving to Q2, then this MOS would be fed with pulses which are not of your Q2 pulse. Okay. Okay. So we will come back to why this MOS is required, why this NMOS is required. The reason I'm calling this as MOS and this is MOSFET is that generally we use the nomenclature of power MOSFET for or MOSFET for power devices and NMOS and PMOS for signal level devices. You can understand that this is a signal level MOS. So that is why the symbol is also different. Principally, you know that this is equal to this, correct? Both of these are same. This is also an NMOS, enhancement mode NMOS, and this is also a MOSFET. But the idea is this is N channel power MOSFET, which is used as a switch for power applications, and this is an NMOS or a signal level MOSFET. Okay. Anyway, so this is just to differentiate between both of these. Okay. So what did we have? We had kind of a current source arrangement, right? So we had a constant current source over here. Okay. So I'm calling this as I charge. Okay, ICHG. Okay, I had a constant current source over here, and the idea is, as I was telling, you need to have a voltage over here, correct? That is kind of a clamping voltage when the device is turned off, and also make sure that the diode gets turned on when Q2 is on, right? Okay. So what did we do? First, we had a current source over here, right? I'm calling this as I charge. Okay. And then what did we do? So we just saw that when Q2 is turned off, right? When Q2 is turned off, so let me write over here. When Q2 is off, then what we saw was that since the NMOS is getting a signal which is a not of Q2, then NMOS is turned on, right? NMOS is turned on, correct? So when Q2 is off, NMOS is turned on. Okay. So when NMOS is turned on, can you tell me what will be the voltage at this point at the V plus terminal of the comparator?
0.
Correct. So when Q2 is off, the NMOS is turned on. So you get V plus is equal to 0, right? So in that case, what happens? Your V plus is 0, V minus is Vref. Therefore, there is no fault that is detected. The output of comparator is logic low and the output of the NOT gate is logic high. So therefore, there is no fault that's getting detected. So one thing you have made sure is that, so you can imagine two scenarios over here. When 400 volts was appearing over here, or whatever is the BTC was appearing over here, right? If you didn't have the diode, then what would have happened? One thing is, of course, due to high voltage, the op amp would have blown off. That is one thing. Second thing is that there will be a false trigger or something that says, okay, there is a fault over here, right? So by making sure that you have this NMOS kind of an arrangement, you're clamping the voltage to 0 at the V plus terminal, right? When the device is turned off. Okay. Right. So this was during the device turn off condition. And when Q2 is turned on, D side should be forward biased, or the diode, the D side, which is the diode, it should be forward biased. Okay. So how do we do that? I need to have a voltage over here, which is more than my VDS, right? I mean, I need to have some voltage, which is kind of a ballpark figure. I know that this is more than my VREF, and I'm dead sure that the device cannot operate beyond this much voltage, right? Okay. So for that condition, we are having a blanking capacitor over here, which is called CBLK. I will come to why this is called CBLK later on, but we have a capacitor arrangement just to make sure, or just to hold some voltage over here. Okay, so now let's consider the other scenario. Okay, when Q2 is okay, so this is the same thing that was explained in the last class. That is that um, when Q2 is turned off, the NMOS is turned on. Therefore, your I charge would be flowing. If I have to take my laser pointer, yeah. So my I charge would be flowing something like this through Q2, correct? So since this is a current source can be shorted, right? So it is kind of flowing like this to the ground and back. Okay, right. So V plus is 0. Okay, fine. So next we came to the scenario that Q your Q2 is turned on. In that case, let's assume that this is a MOSFET and you are operating in the linear region or the ohmic region. Therefore, it can be approximated as a pure resistor. You get a voltage VDS, and the VDS is basically I into RDS. Okay. So I have got some voltage across it, and the idea was to make sure this diode gets turned on. So what did we do? We now have a very simple arrangement for that. Okay. That is, so what people did was we already have this current source over here. Let us add a resistor. I am calling this as RBLK. Okay. Now the idea is that if the voltage at the anode of this diode is more than VDS, that is enough for me. Okay. Therefore, I know what is my I charge. That is it's a constant current source, right? You can realize it with analog circuits, or nowadays it is inherent into the IC itself. So I know what is the value of I charge, and generally the value of I charge is a few milliamperes. Okay, it is generally given in the data sheet of the IC itself, gate driver IC itself. Or you can also realize it with BJT current mirror circuits or CMOS current mirror circuits, right? Okay, so you know what is the value of I charge. Therefore, I can size the value of RBLK so that I charge into RBLK, which is the voltage that appears across this point at this point, will be more than my VDS plus VF. Okay. So, excuse me. Yeah. Hello. Yeah. So as I was telling, what I can do is I can add a resistor. Oh, I can add. Yeah, so we added a resistor over here, right? And we will size the resistor so that the drop I charge into RBLK that appears over here, right, is more than whatever is the VTS plus the diode drop VF. Okay, so now you understand that I charge would be finding a path something like this, correct? As indicated in the blue line, right? So what is your V plus voltage? That is the comparator plus voltage. The comparator plus voltage is going to be I charge into RBLK plus whatever is the forward voltage drop of the diode VF plus VTS, right? So this is the voltage that appears across your V plus terminal, right? Across my V plus terminal means there is a capacitor across the V plus terminal. So this is the voltage that appears across the capacitor, right? Or the capacitor gets charged to this voltage, right? So your V plus is what? This resistor drop plus your diode drop plus whatever is your actual RDS drop. You are actually comparing V plus, that is this entire voltage with Vref. So you understand that in this method, you are unintentionally adding these two drops, correct? That is Vf and I charge into RBLK. But anyway, you can size this, or you can kind of calibrate your Vref so that you can offset this particular drop. But you understand that the comparator operation is actually between your Vref and this particular voltage, that is I charge into RBLK plus Vf plus Vts, right? Okay. And also, since we just saw that the gate for this NMOS is actually going to be the NOT of the gate of your device Q2. So when Q2 is turned on, obviously this NMOS is out of the picture, right? That's why I have struck it out, right? So when the device is turned on, your NMOS is turned off. Therefore, I charge cannot flow through NMOS, right? I charge doesn't get a path through NMOS. It has to flow something like this. You may ask, will it affect normal circuit operation? No, that's why I have written I charge is just a few milliamperes, whereas your device is going to be operating at minimum at least 10 or 20 amperes. So there is not going to be any effect on your device operation as such. Okay. So
But
you understand, right? Your V plus is I charge into RBLK. Oh, I charge into RBLK plus VF plus VDF. So Ravidas, is this fine?
I understood, but one more doubt here. I think there's some portion of the current is means I'm just telling if some portion of the this I charge can go through this capacitor also, and there is a chance this voltage also rise up linearly.
Yeah,
So
yeah, yeah.
V
So
plus will
wait,
be constant.
now you tell me. So I charge. So you forget about the capacitor for now. Okay, forget about the capacitor. Now you understand that just the voltage would be if there is no capacitor itself. The voltage would be I charge into RBLK plus VF plus VDS. Correct. Now I added the capacitor. You know that V plus voltage is kind of a clamped voltage, right? It's a fixed voltage which cannot increase. Why? Reason is that your I charge is fixed, correct? RBLK is fixed. Therefore, I charge into RBLK is a fixed number, right? RBLK is fixed and I charge is fixed. It's a constant current source. VF of the diode, again, it's a fixed number. Okay. And our VDS, again, it's fixed based on the operating condition, right? Because VDS is basically I into RDS, right? Your circuit, you know that, let's say the buck converter is taking 20 amperes current or something like that. So your VDS is fixed, okay? That is I into RDS is fixed. So all of these quantities are fixed quantities, okay? So the voltage over here is clamped, which means that even if you, let's say you now connect the capacitor, then what would happen is the capacitor would simply charge up to this voltage and that's it. Okay, now it's like a I mean, the capacitor is now holding a DC voltage, and obviously you know that the capacitor will not allow a DC current to flow through it if the voltage is kind of clamped. Okay, right? Now it acts like a open circuit. You understand, right? The voltage is
Yes,
clamped
yes,
over
yes.
here
Correct.
at V plus.
Correct.
Okay.
Okay.
Okay. So this is during normal operation if there is no fault. Okay. If there has to be a fault, as I have written over here, then what happens? V plus is obviously is more than V minus, only then a fault is detected. That is I charge into RBLK plus VF plus VDS should be more than VREF, right? Right? So this is the condition at which the overcurrent protection mechanism gets triggered. That is not only VDS more than VREF, additionally these two drops are also getting added up. So what people generally do is you can calibrate if you know what is the value of RBLK you want to use and VF if you know pre-hand, then VREF can be calibrated based on this. Okay. or just we can solve this inequality. Okay, so generally what happens is, if you see the gate driver IC, your RBLK is something that you can change on your own. Okay, so if you solve for what is RBLK, so then your RBLK should be more than or equal to Vref minus Vf minus Vds divided by I charge. Okay, only then your protection mechanism is going to operate. Okay, fine. So till this point, is it fine? So far, we have not yet seen the utility of the capacitor, but do you understand how the overcurrent protection mechanism gets triggered?
Yes, yes.
Okay. Now the next point is, as we were talking about it, what is the role? I'm sorry. What is the role of this capacitor, right? And at the end of the last class, at the fag end, I just told that it is something that's required during the turn off transition. Okay, I'm sorry, during the turn on transition of Q2. So just when you have given the microcontroller pulses to Q2, right? And Q2 was off over here and you are turning it on. So your capacitor comes into play during this transient operation, right? That is during the dV by dt operation. Okay, fine. So let me take up a new page. Okay. So, as I was telling, this capacitor comes into play during the turn on transition. That is, see, now these are the gate pulses. Let me take a different color over here. Yeah, so these are the gate pulses to the device Q2, and immediately the gate pulses for NMOS gets withdrawn, right? So your gate pulse for Q2 is going from low to high, correct? So your gate pulse is going from low to high, and immediately what happens? The gate pulse for NMOS goes from high to low. Okay. So at, let's say, oh, what happened, man? Oh, I don't know why the entire figure got cut off. Okay. Okay. So consider the scenario when the device Q2 is turning on. Okay. So at that point, when Q2 turns on, right? So from the microcontroller, what had happened? From microcontroller, immediately your signal became from a logic low to logic high, correct? So once this happened, immediately what happened is your NMOS got disabled. NMOS got disabled or turned off. NMOS got turned off. Okay, this happens instantaneously. You understand that it's a signal level MOSFET, so it can turn on and turn off very fast. Okay, but how would it come to Q2? So then what happens is your if you see the realization of the circuitry behind this part, that is before the gate part. So we know that we have a gate driver over here, So this is your gate driver IC. Okay. And within this gate driver IC only this entire circuit is there. Correct. But over here is where you have, so let me draw. So you are giving your gate pulses from microcontroller. So output from microcontroller or the pulses from microcontroller are coming over here. So let's consider that this is an isolated gate driver, and in that case, you will be having something like this. So on this side, let's say this is the signal ground. Okay, and on this side, you'll be having the reference to the power ground. Okay. So your microcontroller pulses are with respect to the signal ground, not with respect to the power ground. Obviously, there is an isolation that's provided by the gate driver IC. We saw in the last class that isolation can be, I think in the last to last class, that isolation can be either optocoupler based isolation or capacitor isolation, or it can be on a transformer based isolation. But anyway, that is going to be some isolation. So what happens is, for this, if you have isolation schemes, then the time or the propagation delay within the gate driver IC is high, okay, due to the isolation. So for the same gate pulses, you have given the gate pulses over here with respect to the microcontroller ground. So for the gate pulses to be converted to a signal which is respect to the with respect to the power ground, there will be a propagation delay within the gate driver IC. Okay, so there will be a propagation delay. Propagation D. I just hope it has not. So propagation delay within the IC. Okay. So this propagation delay can be of the order of a few tens of nanoseconds. Let's say around 50 to somewhere around 80 nanoseconds. Ballpark figure, okay. Between 50 to 80 nanoseconds, somewhere around this, there will be a propagation delay. Okay. And then what's happening? So then you are feeding it through a gate resistor, right? Which is called RG. Through a gate resistor, you are feeding the output from the gate driver. You are feeding through a gate resistor to the device Q2, right? This is the circuit. So this is your device Q2. So what happens is there will be a propagation delay initially, and then over here, let's say you get a logic high pulse over here after the propagation delay and after isolation. So this is before the gate resistance, and after the gate resistance, what you would see is, because of the presence of this gate resistance, there will again be a delay, and you will see something like this. Correct? So there is going to be a delay. Why? Because you understand that there will be, so your effective, yeah. Oh, so your effective circuit is going to be something like this. Correct? This is your RG, and this is your CISS of the MOSFET. Okay, this is what you are going to get at the output. Okay, I know, I don't know what's happening over here. Anyway, I hope you understand that. Okay, so the effective circuit we saw was something like, yeah, okay, so the effective circuit is again an RC kind of a circuit. Okay, you know that again an RC circuit is going to induce some delay, right? With a time constant tau is equal to RG into CISS. Correct? Did you get this? That is, there is going to be a delay, right? From the time you give, let's say, at t is equal to 0, you have given a logic high pulse from the microcontroller. When it actually gets reflected to the device that there is a logic high pulse, there is actually some delay, right? There is a delay. Let's call this as TD. Okay, so did you understand, both of you, why this delay is happening?
Yes, sir.
Okay, so the idea was, if you have this as the pulse from microcontroller, what you might be seeing at the gate of the device is something like this, right? So there is going to be a certain delay TD, which is dependent on the propagation delay within the gate driver IC and also the delay induced by the RC circuit that's formed in the gate drive, right? That is between the RG and CISs. Okay. Okay, so this is, let's say, at t is equal to 0. But at t is equal to 0 only, you're feeding the pulses to the NMOS. Correct? Now the point is, since this is a signal level MOSFET, right, it can turn on and turn off really fast. It is not like the power MOSFET, which takes some time. It can turn on and turn off in sub nanosecond level. Okay, so you might see that the MOSFET would see, we know that the MOSFET has a knot of your gate pulse, right? So your gate pulse, when it is, I'm sorry. So this is your microcontroller pulse, right? So this is your microcontroller pulse. This is at the gate of Q2, right? But what would happen is the NMOS would be seeing a pulse, logic high to logic low pulse somewhere over here itself in between. Okay, this is NMOS pulse. So you see that there is a definite time over here, right? There is a definite time over here during which your NMOS gets kind of disabled. Okay, do you understand this? There is a specific time during which NMOS is getting disabled, right? Do you understand, both of you? There is going to be a
Yes, yes,
specific,
sir.
yeah. So there is going to be a specific time duration for which your NMOS is going to get disabled. So this is one point. Okay, fine. So the next thing logically you should ask is what happens when you give, even over here, right? Even over here you have given the pulses to the gate of Q2. So only after you give the pulses, what happens? Just after you give the pulses. So if you can recall how the device turns on, you would remember that we also saw this in the double pulse test previously, right? So we saw that, yeah. So what did we see? If there is a logic low to logic high pulse as shown over here, if there is a logic high to a logic low to logic high pulse, then your VDS falls from 400 or whatever is the VDC to almost zero, not exactly zero. You know that it's going to be I into RDS, but your VDS falls. Okay. And if you kind of zoom in over here, right? If you kind of zoom in over here, you will understand that the VDS falls only after your gate source voltage has increased, right? So going back to this particular figure, yeah. So let's say that you have got gate pulse in that device, something like this. So this is your logic high pulse to the device Q2. Okay. This is your VG, as I call it. Okay. So how would your VGS look like? Your VGS is going to slowly increase and then reach over here. Okay. So this is how your VGS is going to look like. This is VGS. Okay. Now the idea is that your VDS will start falling somewhere over here and then go to zero, right? Is this fine? Your VDS was VDC previously and it will go not exactly to zero as you know, but it will go to your on-state VDS on-state, right? So there is a voltage fall when the device turns on. And when is this voltage fall happening? The voltage fall will happen after your VGS comes into effect, right? Obviously, right? Makes sense. Only after your VGS has crossed V threshold and all, and only after this point is your voltage going to fall, right? Do you understand this? Your voltage will fall only after you give the gate pulse to the device, right? Correct? So you understand that if you include this time as well, there is going to be a specific period starting from this point to this point, right? So if I can complete the waveforms over here, your VDS is going to kind of fall something like this, correct? So this is my VDS. It was initially VDC and it falls to VDS on, or a low voltage, whatever, somewhere near zero, or I can call this I into RDS on. Okay, so your VDS is going to fall from VDC to almost zero, right, over here. So you understand that there is a specific time duration. Okay, there is a specific time duration, that is this interval, during which the voltage across the device is very high. Okay, VDS is very high. Do you understand this? Is this fine?
Yes, sir.
Okay. So now let's analyze the circuit, DC circuit during this interval. Okay, that is, so now what has happened at this instant itself, your NMOS has turned off. Okay, so the NMOS is now out of the picture. This NMOS is now out of the picture. Okay, so this NMOS is out of the picture, right? Therefore, what would happen? And your voltage is very high over here, right? Your voltage is very high. So let me copy this once again. Oh, it's getting copied with this. Probably again I need to draw. I don't know. Um, anyway, so it's better I take some time, so no worries. Um, okay, so this is the circuit. Now we are talking about this particular instant, right? Let's say this is at t equal to t1, and let's say this is t equal to t2. Okay, so during t equal to t1 to t equal to t2, so between t equal to t1 to t2, we saw that VDS is very high. Okay, so one, VDS is very high, right? And two, your NMOS is turned off. Okay, so we saw in the starting itself that when the device is completely off, your um, current source will find a path through NMOS, right? It will find a path through NMOS. if the NMOS is, since the NMOS is turned on, your voltage at V plus terminal is clamped to 0, right? Voltage at the V plus terminal is clamped to 0. Okay. Now the point is that same thing, but NMOS is turned off, right? VDS is still high. The voltage across the device is still high, right? But NMOS is now out of the picture. Okay. So NMOS is out of the picture. Okay. And your VDS profile is something like this, right? It was VDC and then it will fall to almost 0, then somewhere near 0, very high value. Okay. So during that time, right, again, this DSAT, the diode is going to be reverse biased, right? Diode will be reverse biased. So there is no direct connection as such. So then what would happen if I can draw the equivalent circuit? So diode is reverse biased, voltage is still high or it is falling, but still we know that the diode will not get forward biased until the voltage at this point exceeds your VDS, right? So diode is obviously reverse bias right now. Okay. So can you tell me how would I charge flow? What is the path for I charge now?
Through capacitors.
Yes, through the capacitor. Why cannot I charge flow through the to this 2 plus terminal of the op amp? Why can't it flow?
Where, sir?
Why current cannot flow into the op amp? Can current flow into op amp?
Amp. Mm,
Yeah, so the answer is that op amp is
V
ideally
reference.
if you see op amp which should not take any current, right? So that is why no current flows into the op amp. Okay, so entire current would be flowing through the capacitor during this period between T1 to T2 when the voltage is still high. Okay, during this period. So T1 to T2. Okay, fine. So now what's happening? A constant current is flowing into the blanking capacitor or CBLK. Okay, so you know how would the voltage across the capacitor increase now? Can you tell? Would the
Linearly.
increase be linear, quadratic, or it will be a ramp, or how would the voltage increase?
Linearly.
Yes. So the idea is I is equal to C dV by dt, correct? So your I is simply I charge over here, and this is CBLK into dV by dt. Therefore, the voltage across the capacitor, right? Since dV by dt is constant, your voltage is increasing linearly, right? You can find out also by integration. You can just find out if you assume that since initially the voltage was 0, right? The initial condition is 0. Therefore, you know that I charge by CBLK into T, right? Integral dt and initial condition you need to add. Since initial condition, initially the voltage across the capacitor is 0 because NMOS was turned on previously. So the voltage is 0. So the voltage is going to increase something like this. So between T1 to T2, right? That is the voltage at the end of T2 would be equal to, let me call this as VC. So the voltage would be equal to I charge by C BLK into T2, right? So this would be the voltage across the capacitor. Okay. So now what happened is at T2 or beyond T2, what happened was the VDS reduced to such a low level or such a very low level that this diode got forward biased. Okay. VDS increased to such a VDS decreased to such a low level that this diode got forward biased. Okay. Then at that point, the voltage would get clamped to whatever is the voltage that we saw earlier. Did you understand this so far? So the CBLK is kind of a mechanism that provides or that allows the voltage to increase during this period. Okay, so VC and this is equal to V plus as well. Okay, fine. So now this is the voltage that appears at the plus terminal of op amp or the comparator. Now you tell me during this period, do you want the op amp to get triggered or do you want the op amp to be turned off or the comparator to operate or not? Did you understand? So during this period between T1 to T2, right, we saw that the voltage is going to increase from 0 to some value, right? V plus is going to increase from 0 to whatever is this value, right? So during this period, do I want my comparator to operate or no? Did you understand the question? Ravidas and others. So during this period, that is between T1 to T2, we saw that the current is going to find a path through the capacitor, right? And the capacitor voltage kind of increases linearly. So during this period, what is happening? The diode is reverse biased, right? So during this period, I don't want my comparator to operate because the voltage at the comparator is not directly VDS right now because the diode is reverse biased, right? I charge is finding a path through the capacitor. It is just helping me to rise the voltage or ramp up the voltage, right? To this point. Okay. So I don't want my comparator to operate during this region, right? Therefore, I can select my value of CBLK so that for the entire duration till T2, entire duration, I will make sure that this voltage remains lesser than Vref. Do you understand? So that the comparator doesn't operate. Did you understand this? Ravidas and Selvakumar sir and Aditi.
Sir, whenever that V plus is less than the Vref, the output of comparator will be always low only. No?
Normal only. So we want to make sure that during this transition between 0 to T2 or T equal to T1 to T2, right? During this period, your diode is anyway turned off, right? The diode is
Yes.
anyway turned off. So we are not getting a sense of what is the actual voltage across the device, right? So during this period, I don't want my comparator to operate because now the comparator is actually not getting the actual VDS, right?
Yes.
Correct? So I
Correct.
have to make sure that I have the capacitor over here, right? I have to make sure that the voltage increase during this period doesn't go so much high that this voltage becomes beyond Vref. Do you understand?
Yes. Yes.
Right? So you have to make sure that your VC should always be less than VREF.
VREF.
Yes. So that you can prevent spurious triggering of the comparator. You don't want the comparator to kind of false trigger. Okay, it should not sense that, oh, there is extra voltage at V plus terminal, and it should not give a fault signal. You understand, right?
Yes, sir.
Okay, fine. So, this period between 0 to T2, right? So, this is a period during which your circuitry is kind of disabled, right? Correct? Because at t equal to T1, or let's say at t equal to 0 itself, you have given the gate pulses to the device. Okay, at t equal to 0 itself, you have given the gate pulses and the NMOS is turned off. So ideally, or technically speaking, from this moment itself, the device is turned on. Okay, and ideally, we told that from the starting itself, I want my comparators, I want my protection security to be there, right? From the instant at which the device is turned on, from that point itself, I want to check for protection always. But you see that due to constraint in the device voltage, that is VDS being very high and all, and we saw that VDS falls only after certain period of time, we see that what happens, the protection circuitry is going to come into play only after T2, right? Whereas we had given the gate pulses at t equal to T1 or t equal to 0 itself, we have given the gate pulses, right? From the microcontroller, we have given at t equal to 0 itself, right? You get reflected at t equal to T1 itself, the device is kind of turned on. You have given the pulses to the device. However, because you have to wait for the voltage to fall, right? You have to wait for the voltage to fall, and that takes some amount of time. So this time, the voltage fall time can be around 50 nanoseconds or 100 nanoseconds, something like this, right? So it takes certain amount of time for the voltage to fall, and only after the voltage has fallen to a much lower level, the protection circuitry is kicking in. Do you agree?
Yes, sir. But
Right.
we can reduce that propagation delay such different way. Then it will happens that
Fine. So your propagation delay is reduced. Even after that, you have to wait for, let's say, propagation delay is 0, right? Ideally, let's take propagation delay inside the gate driver is 0. But beyond the gate driver also, we know that, right? So this is the point at which the output
uh,
from the
uh,
gate driver.
yes, RG and the C, that combination delay
Yeah,
will be there.
so because of that, it will take some time for the gate voltage to rise, and beyond, after your gate voltage starts rising, only your VDS will fall, right?
Okay, okay,
So
correct.
again, you see that even if you see over here, right, this is your T equal to T1 point, whereas this is your T2 point, right? Exactly, right? If you discount all the propagation delay and all, still inherently due to the device characteristics, you see that there is a delay. I mean, there is not a delay, there is kind of a time interval between the point at which you give the gate pulse and the point at which your VDS actually falls to a very low value. Do you agree? That is, this
Yes,
is
sir.
the T1 to T2. So
Yes.
this period is called blanking time. Okay. This period is called blanking period or blanking time. So during the blanking period, your capacitor kicks into play, right? CBLK kicks into play. That's why it's called blanking capacitor, because during this period only your I charge will flow through CBLK. Okay, and the voltage increases, and you will size your CBLK so that your voltage should not increase beyond VREF. That is, your VC should be less than VREF, right? You will increase your CBLK value so that your VC will be less than VREF. Agreed. This is one. Second, ideally, since you have given the gate pulse over here, I want my protection also to be in place from t equal to T1 itself, right? But unfortunately, since we rely on VDS value, and VDS value goes to a very low value only after T2, till this period from T1 to T2, your protection circuitry is not connected. Agreed, right? Because your diode is reverse bias till this point, till T2. Do you
Yes,
agree?
sir. Yes, sir.
Right. So this is one of the drawbacks of DSAT protection scheme, right? Because you're relying on VDS. You're not directly sensing the current, you're relying on VDS. So let's say in between T1 to T2, there is a short circuit fault. Okay. So there is a short circuit fault in between T1 to T2. So your short circuit current, let's say it started increasing from here rapidly. You will be able to sense this only after the T2 point. Okay, fine.
Yes,
So
sir. Correct.
this is called blanking period. Okay. So for this blanking period amount, the circuitry is disabled, right? You cannot have this circuitry. Okay. Oh, we have spent almost 1.5 hours just to understand DSAT, but I think this wraps up kind of the DSAT operation. So, do you have any doubts so far? Just I will kind of list some key points in another slide. Okay. So, if I have to list down some key points, one is that under normal operation, right? And when Q2 is fully on, your V plus is I charge into R BLK, right? Plus forward voltage of the diode plus your VDS, correct? And V minus is simply V. So you compare V plus and V minus. This is one. Second, what should be the rating of the diode is the next question, right? What should be the rating of the diode? Can you tell?
More than V bus or VDC, whatever you apply across the
Correct.
bus.
Correct. So your voltage across the diode DSAT, DDSAT, right? So the voltage rating for the diode should be more than VDC. Okay, at least take 1.4 or 1.5 times, right? 800 volts DC bus. If you have, then you have to have a diode that's rated for 1200 volts, something like that. Okay, and three, we just saw that your capacitor voltage, right? VC should be less than VREF during the blanking period. So during blanking period, your VC BLK, you should ensure VC BLK is less than VREF. Okay. So VC BLK is simply what? VC BLK is I charge by CBLK into T should be less than VREF. T BLK or T2, whatever you want to call. The time interval is T BLK. Okay, you should ensure this. Therefore, you will size your capacitor accordingly. Okay. Therefore, your CBLK, your inequality changes obviously, right? So CBLK should be more than IREF into TBLK by EF. Right? Okay, is there anything else? I think they have covered all. When Q2 is fully turned on during the blanking period, yeah, and when Q2 is off. So what should be the rating of this NMOS? What should be the voltage rating for NMOS? What is the voltage? So you will see the NMOS voltage when NMOS is out of the picture, right? So your NMOS should be rated for V plus. So NMOS rating voltage should be more than V plus, right? And the current rating for the NMOS should be more than I charge. I charge is anyway very small, so doesn't matter. Okay. And mostly you will not be using an external NMOS. So these are internal to the gate driver IC itself. So you need not worry about this that much. Okay. Fine. So I think at this juncture I would show you commercial gate driver IC from Texas Instruments. I think that should give you an idea. Okay. So I will just search for UCC. Let's say this. Okay. Are you able to see my screen?
Yes, sir.
Okay. Yeah. So this is 10 ampere source and sink isolated gate driver IC, right, with protection circuitry and all. Let's see. Okay. I think they will give a typical application diagram, right? Yeah. PW interlocking fault pin. Automatic reset. I'm not sure if it has the current computation. Yeah, Miller clamp. Yeah, short circuit protection. Yeah, so protection, this is what I was referring to. Protection based on desaturation circuit. You can go through this, okay? I think, yeah. So as we were talking, see, this is the comparator, right? And internally the reference is being set to 0.7 volts. This is the NMOS we were talking about, right? NMOS has a control logic, and we saw that the control logic is something like the NOT of your whatever is the gate pulse for the device, right? Externally, you will add the diode. Okay, so you have to purchase, let's say you have a 800 volt application, you have to purchase a 1200 volt diode and externally put it. This is the DHV. Okay. And similarly, there will be RBLK. Yeah, so there is a CBLK as well that you need to put externally. So you understand that beyond these terminals, all of these are external components, right? That is RF, R1, all these are external components. So externally, you will have to connect the blanking capacitor, CBLK, DHV, right? And I don't know which among this is exactly RBLK. I think you can go through the data sheet one. So you understand that you have control of what is CBLK, you can have control of what is RBLK. So even though your reference is fixed at 0.7 volts, you can change the reference current for threshold, right? So yeah, so you know that your VDS is I into RDS. So let's say I want to set the fault. So this is the actual device current, right? This is the actual device current. So let's say I want I to be set at 40 amperes, right? You can solve this inequality and arrive at a correct value of RBLK. Okay, because VREF is set to 0.7 volts, right? VREF is set to 0.7 volts. If you see the data sheet, I think they have mentioned what is I charge, right? You will know what is VF and you know what is RDS. So for a particular value of I, you will know what should be the RBLK. Okay, is this fine? I think probably I will solve a numerical example, but
Okay, sir.
is this, is this
Is this
fine?
driver capable of 5 megahertz switching?
Capable of 5 megahertz switching.
Yeah,
So what is the idea behind that number 5 megahertz?
means some application is there. That's why.
Okay, so 5 megahertz will
Generally,
you be doing?
which term is basically you are using for looking for the switch? I mean, switching frequency operation. Generally, nowhere actually mentioned, but generally some 100 200 kilohertz only some data is given generally, na? But actually, at what maximum switching frequency it can
See,
operate for that? What thing?
first things first, I'm dead sure you will not be using SAC MOSFETs or IGBTs at 5 megahertz, right?
Yes, GAN only, GAN MOSFET only.
Yeah. So for gallium nitride, you cannot use this driver first of all because this is exclusively for SIC and IGBT. The reason being that the gate voltage it doesn't support the gate voltage required for GAN. For GAN, you know that the gate voltage will be probably up to 5 or 6 volts depending on the company that you use, right?
Yes, yes.
Right. So this UCC 21732 I guess supports for VDD and VE of plus 15 minus 5 plus 18 minus 3 something like that. Okay, it has an UVLO up to 8 volts or something. So obviously you cannot use this for GAN.
Yeah,
Okay,
got
but
it.
but with SIC itself, if you want to go for higher and higher frequencies, let's say with SIC people have gone till easily 500 kilohertz or even 1 megahertz. Some people have gone. So in that scenario, what happens is since you are going to high frequencies, you need to have very high dV by dt. That is, your turn on and turn off times will be very small. In that case, your dV by dt will be very high. They have told that the common mode transient immunity, right? I have highlighted it, yeah. So the common mode transient immunity is 150 volts per nanosecond. That is, it can support a dV by dt of up to 150 volts per nanosecond without significant leakage. Okay, so you cannot obviously go till 150 volts per nanosecond, but as a ballpark, you can go probably till around 30 or 50 volts per nanosecond. So that should give you the limit on maximum frequency that you can achieve. Do you understand?
Yes, but generally, other than this is basically for SIC and IGBT. For example, generally other drivers also, whatever we have for the GAN purpose, I'm telling. For that means what parameter should we check for maximum switching
Yeah, so you
operation?
should look at
Generally, most of
CMTI.
the time.
Yeah. So you should look at CMTI. CMTI is one of the very critical parameters. Okay.
See, for
Second,
example,
you can look.
CMTI, I have one integrated gate driver of GAN that can support it of almost 100 volt per nanosecond. Okay. For that, if I want any isolator, that should be more than this. Okay. But if within this,
Yes.
other than this, if I want only discrete, for example, I have one GAN system driver, means GAN system power fail, and any other like Skyworks or Silicon Technology driver. For that driver, if I want to choose for that purpose, what is the switching frequency? For that, what thing we should see?
You want to choose the driver or you want to choose the switching frequency?
This driver which can support at least 5 megahertz of switching frequency for GAN MOSFET.
Okay. So, yeah, so you have to basically look at two, three things. One is CMTI is a must that you should look at, right? Your CMTI should be 3 to 5 times minimum. Okay. That is one.
Okay.
Second, you will look at what is the maximum current that it can support. Okay. Because the idea is since you will be driving at a mm, very high frequency, the gate current requirement and of course the gate power requirement will increase, right? So can you tell how do you calculate the gate power?
Can I tell you the part number from there? Can you a little bit? Can you explain?
Yeah.
Yeah, you can search SI. Just what is it? SI
It
8274.
was,
Yeah,
yeah, I think this is Skyworks, right?
Skywork. Yeah.
Yeah.
With this, for example, I want to drive MOSFET of this GS 66504.
Okay.
Okay, at 5 megahertz. So is this combination is good at 200 volt something bus voltage half bridge configuration?
The idea is, I think it supports good dV by dt immunity as far as I remember. Yeah, so 200 kilovolts per microsecond it can support. So I think this is good enough, right? And what about the peak current that it can drive? I forgot the exact number. Peak current, I think it can support up to 4 amperes or something, if I remember right.
Current requirement is not that much. 2 amps also it is fine actually. With this it will okay.
Okay, so current requirement. Yeah, then you can, I think you can use
But
this.
switching frequency, I am doubting actually.
Frequency, I don't think they specify what is the switching frequency as
Yeah,
such, right?
nowhere actually generally they don't mention this maximum switching frequency of any driver.
Because
For that
that's not
any
required, right? It's obvious after all a gate driver. So the thing is this only dV by dt immunity.
yeah.
Okay, so I think you can use this. To be fair, I think we have used this in our lab for other applications, but so far it has worked fine. So yeah, I think you can use this.
Okay, this one
This
already you have
status.
used any other application? Means
Yeah, so
what
this
is
is
the
4 ampere driver, if I remember. Yeah,
yeah, yes,
this is a 4
yes.
amp driver. Yeah, it can be used. I think it gives good. It has isolation, opto based isolation as well, right? Opto or capacitive isolation.
I
Exactly.
think
I think
semiconductor
it's
based, I think. Or maybe
capacitive isolation or opto isolation. I exactly forgot what isolation it uses, but
it
I
is
think it
basically
can be used.
semiconductor based actually. Yeah, this is your
No, no, the
opto.
isolation.
Isolation is your this one only, optocoupler based only. They have mentioned a semiconductor based isolation.
Semiconductor
Yeah.
based isolation. Okay.
Mm-hmm.
Yeah. So you can use this. It's not a problem.
Okay, we'll see then.
Yeah, I can check. Actually, this IC has been tested. I think you can refer to some research papers, but as far as I remember, there people have gone to high frequency with this in megahertz level up to 6 or 7 megahertz. If I remember, I saw some papers. I was reading up some papers. I think
Okay.
they have gone with SLE 827 ICs.
Okay.
Okay, fine. So I think we should come back now. Yeah, so I was talking about this UCC gate driver IC. Okay, so how do I set the value of RBLK? So we saw that with RBLK you can control what should be the fault threshold current. Okay, so what do I mean by that? So let me take a new slide. Okay, so from UCC 21732 IC, right? We saw that Vref is zero point 0.7 volts, right? Vref is 0.7 volts. Okay, so let us refer to that IC itself and find out what is I charge. I'm not sure if they would give the exact value for I charge, but it is generally a few milliamperes. So even if they haven't given, it's not a problem. We can just assume some value. I think we have to do a bit of searching before we get it. Okay, so you can go through it and see what is the exact value, but let's assume that my I charge is somewhere around 3 milliamperes. Okay, a very low current I'm assuming. Okay, and what else is required? Yeah, So let me assume that my VF is going to be around, let's say this is 0.25 volts. Okay, some figure, right? So VF is 0.25 volts. And RDS on is, let's say, 20 milliohm. Okay, RDS is 20 milliohms. In that case, the question is design RBLK so that the fault threshold current, right? The fault threshold current is A 30 amperes, B 70 amperes. Okay. So you have to, if you vary RBLK, you can vary your fault threshold current. Okay. So let's go back to the basics. We know V plus should be more than V minus in the case of a fault, right? V plus is simply I charge into RBLK plus VF plus VDS is basically I into RDS on should be more than V minus is VREF, right? So solve this inequality, you get RBLK should be more than VREF minus VF minus I into RDS divided by I charge. Okay, fine. So just substitute the parameters over here and um, you should get the answer. Okay. So will you guys do this or should I do? So let me do for one.
Well,
Sorry, did you solve this? What should be RBLK in first case and what should be RBLK in the second case? Can you solve and tell? I think it will be of the order of a few kilo ohms if so VREF is 0.7 minus 925 minus 5 into RDS, right? So 13. Okay, so I think kind of we have assumed a very high value for VF and all, so it's better we reduce it. Okay, so instead of 0.25, let me take this as 0.1 volts. Okay, so to clear this, so you get VF Yeah, okay. So one more thing that I wanted to mention was, so far, before you continue with the calculation, right? One more thing I wanted to mention was, so far we have seen something like this, right? That is directly across the device you have connected it. Okay. And we saw that, let's say if VA, even if VF is 0.25 volts or something, which is a very practical number. So um, even if VF is 0.25 volts, right? So then what you would see is this inequality kind of doesn't hold good, right? That is your VF and IRDS will be way higher than your VREF, right? So what people do is instead of directly connecting it, you can have a resistive divider, okay? So you can have a resistive division circuit and then connect across this, okay? and then you connect across this. Okay, so you will connect to this point. So basically you are sensing what is VDS into whatever is the ratio of the resistive divider, R2 by R1 plus R2. Do you understand? We step down the voltage. Okay, that is also done. Directly we do not connect it to the drain source terminal. Okay, you can connect it if you want, but I think in most of the practical circuits, people have this kind of a resistor step down circuit so that you bring it below the range of your VREF. Do you understand this? Is this
Yes, sir.
fine? Okay, so let me tell that the VREF step down ratio, right? So step down ratio is, let's assume the step down ratio is 1 by 5. Okay, I'm stepping down the voltage to 1/5, right? So this I into RDS is going to be 1 by 5. Okay, so you take this into consideration and then you solve. Did you get it? Towards the end, we just added this resistive divider, which I did not mention earlier. But okay, apart from this, did you understand the functioning of the DSAT circuit? That is, we started with comparator, then we added the diode for reverse voltage blocking. Then we saw that we had an NMOS circuit, that is an NMOS whose gate is opposite to the gate of the device, so that the NMOS is turned on when the device is turned off, and it maintains the voltage at the comparator as 0 when the device is off. And then we saw that when the device turns on under steady state, the voltage would be something like this, that is V plus. And so obviously this is VDS by step down ratio. Okay. And um, during the transition, that is during the blanking time, there is a capacitor across which the voltage increases. You need to make sure, or you need to size the capacitor appropriately so that your um, voltage doesn't exceed or your voltage doesn't exceed your VREF to avoid false triggering of the protection circuitry, right? And in the end, we saw that we directly do not connect it. We generally have a step down mechanism. Okay, so you can just solve. I have just taken some random numbers, but this is how you generally design the circuit. Okay, and we saw that the reference value and the I charge are something that's internal, that is to the gate driver, right? And your RBLK, CBLK, and the diode are some things that you connect it physically outside the terminals of the gate driver. This is fine. So this concludes the discussion on DSAT. So do you understand what is DSAT and its functioning? Like Ravidas and Selvakumar sir, is
Yes,
this
sir.
fine?
Yes, sir. Yes, sir.
Okay, so I think it is already time. So I will not start the next topic now. In the next class, I think we should see a bit about dV by dt protection, right? How do we connect, how do we protect the circuit against high dB DTs? What are the technique for that? And yeah, so that is something that we'll see in the next class. But before we conclude, I would just touch upon another protection scheme instead of DSAT. So one of the drawbacks is that apart from you requiring a high voltage diode, right, and a blanking capacitor, you see that effectively the protection is not enabled during the blanking time between T1 to T2, right? Between the blanking period, there is no protection. If there is a short circuit during this period, that's going to be catastrophic, right? Because your protection circuit will kick in only after T2. Okay, so that is why instead of relying on VDS, people thought, why not we directly sense the current? If I can directly sense this current, I need not even rely on VDS and have such a circuitry at all. Okay, so this is why people came up with this circuit. That is, you know that there is going to be parasitic inductance due to the trace. Okay, that is, we call this as the trace inductance. So directly I will sense the voltage across this trace inductance, that is L into di by dt. Okay, and then I will compare it with some value, right? Or I'm sorry, so you will sense the trace inductance and then you will integrate it. So I will integrate L di by dt. What do I get if I integrate L di dt? I will get a sense of whatever is the current I of t. So after I integrate it, I can compare it with the reference value or the reference current. Do you understand this? This is di by dt integration. So here the integrators realize using this arrangement, kind of an RC arrangement. You know that, kind of like a high pass filter. So this is kind of an integration mechanism. So
This
instead of this,
parasitic inductance is part of the circuit, correct, sir?
yeah. So this is not an
Oh,
external inductance that you add.
okay,
Okay, this is
external
not an
inductance.
external inductance. This
It is,
comes because there is a physical connection because of the traces.
yes, trace, PCB
Okay.
trace. Okay.
Yeah, because of the PCB trace. So if you sense the volt, so let's say that this is your MOSFET. You have 3 terminals, right? And let's say this is the source, and this is your negative DC terminal, right? So you will be having a PCB trace that connects this source terminal to the negative DC terminal power source. Okay, so now because of this trace, right, this trace would be having a very small parasitic resistance and the parasitic inductance. We are sensing the voltage across this. This is the LDA by dt, and I will give this. So here in the circuit, I think they have used a passive integrator, that is an RC arrangement. Better way, instead of using an RC arrangement, you can give it to an op-amp integrator. Okay, so you can give it to an op-amp based integrator. So this will be the minus plus terminal. Okay, so this is R, and then you will have a feedback capacitor. Yeah, so this is an op-amp based integrator. Now you have the comparator. This is VRF. So this VRF is directly proportional to the fault current reference, I reference. Do you understand?
Yes, sir.
Okay. So how do you set the value for VRF? You know that the output of integrator is 1 by RC, correct? V int, if I call it, the output of integrator would be 1 by RICI, whatever is the integrator RC value. Okay. So V int is 1 by RC into whatever is VLS. Okay. So this is your V integrator. You will set the reference current, I reference, proportional to this based on this scaling. Do you understand this?
Yes, sir.
Okay, okay, thank you. So, Ravidas, is it fine so far?
Yes, yes. Okay.
Okay. So, okay, so I think we have covered enough about overcurrent protection across 2 complete sessions. So I think we will stop over here. I will again upload. You can go through the problems, right? Most of them are theoretical, but you can go through the problems in the next class. I will try to frame some numerical problems as well instead of just saying theoretical problems. Okay, so we have learned a bit of math over here as well. So we will try to solve those from the next class. So I think we will conclude over here. And thanks for hanging around. And good night, and have a great week ahead.
Excuse me. Hello. Excuse me.
Yeah, yeah.
Yeah. Can you please tell in IIT Delhi which professor is working in this field actually? Means under you are
In
doing
IIT Delhi, which
in IIT Delhi means who is actually doing this works in high power high MOSFET things? Which professor actually?
in which professor is working on high frequency?
No, not high frequency. In these high power devices.
I'm not getting your voice is very breaking. On high power?
Hello, is it audible now?
Yeah, tell.
Yes, yes. I from who is actually working in this field actually in IIT Delhi. Actually, I don't have any reference.
Okay, so I am actually working on gallium nitride devices. Okay, so mostly
Okay.
there are three professors as far as I know. My own two supervisors are working on gallium nitride devices and high frequency power applications. Okay,
Okay.
so in our lab we are using the similar gate driver that you just mentioned. Okay, that is the SI827 gate drivers. Okay,
Mhm.
and there is so if I have to name my professors, just hang on a second. I will.
Mhm.